Welcome to CosmicHuntX, where we explore the secrets of the universe and beyond. In today's episode, we have a mind-blowing discovery that will change everything we know about black holes. Scientists have found a new type of black hole that has never been confirmed before. This black hole is hiding within the Messier 4-star cluster, one of the closest globular clusters to Earth. It has a mass of about 800 times the mass of the Sun, making it an intermediate mass black hole, or IMBH for short. But what are black holes? And why are they so amazing? Black holes are regions of space where gravity is so strong that nothing, not even light, can escape. They are formed when massive stars die and collapse under their own weight. Black holes come in different sizes and masses, depending on how they are born and how they grow. The most common types of black holes are supermassive and stellar black holes. Supermassive black holes are the biggest and heaviest type of black holes. They have millions to billions of times the mass of the Sun, and they sit at the centers of most galaxies, including our own Milky Way. Supermassive black holes are thought to be the engines of galaxy formation and evolution, as they shape the environment around them with their immense gravity and radiation. Stellar black holes are the smallest and most numerous type of black holes. They have up to 100 times the mass of the Sun, and they are scattered throughout the galaxy. Stellar black holes are born when massive stars explode in supernovas, leaving behind a dense core that becomes a black hole. But what about the intermediate mass black holes? These are the rare and mysterious type of black holes that have been predicted to exist for decades, but have been very hard to find and verify. Intermediate mass black holes fill the gap between supermassive and stellar black holes, having hundreds to thousands of times the mass of the Sun. They are believed to exist mainly within the cores of globular clusters, which are dense systems of stars that orbit around galaxies. Globular clusters are ideal places for potential IMBHs because they have many stars in a small space, creating a high-density environment that could lead to frequent collisions and mergers of stars and stellar remnants. These collisions and mergers could create IMBHs through a process called runaway stellar collisions, where a massive star grows by swallowing nearby stars until it becomes a black hole. However, finding IMBHs within globular clusters is not easy, because they are very dim and emit little or no light. Moreover, most globular clusters are very far away from Earth, making it difficult to observe them in detail. Previous attempts to find IMBHs within globular clusters have relied on indirect methods, such as looking for X-ray emissions from gas falling into the black hole, or measuring the speeds of stars orbiting around the black hole. However, these methods have not been conclusive, as they could also be explained by other causes. This is where Hubble comes into play. Hubble is one of the most powerful and famous space telescopes ever launched. It has been orbiting Earth since 1990, and has made countless discoveries and observations that have revolutionized our knowledge of the universe. Hubble has a unique advantage over other telescopes. It can observe invisible light, which is blocked by Earth's atmosphere. This allows Hubble to see things that other telescopes cannot see. One of the things that Hubble can see is the Messier 4-star cluster, or M4 for short. M4 is one of the nearest globular clusters to Earth, located in the Scorpius constellation. It contains about 100,000 stars, and has an estimated 800 solar masses at its core. This raises questions about what kind of object could account for such a large mass concentration at the center of M4. To answer this question, scientists analyzed 12 years of data from Hubble, which tracked the precise movements of 6,000 stars within M4's core. They also combined this data with information from Gaia mission, which measured the distances and positions of billions of stars in our galaxy. By combining these two datasets, scientists were able to create a detailed map of M4's core and calculate the gravitational potential that influences the motions of its stars. What they found was astonishing. The stars in M4's core were influenced by a dense mass of nearly 800 solar masses at the cluster's center. This mass was much larger than any single star or stellar remnant that could exist in M4. Moreover, this mass was not emitting any detectable light that could indicate its nature. To determine if this mass was a single IMBH or a collection of smaller objects, such as neutron stars or white dwarfs, scientists looked for high-speed stars that could be linked to a potential IMBH. High-speed stars are stars that move faster than expected due to gravitational interactions with a massive object. If there was an IMBH at M4's core, it could sling some stars away at high speeds as they pass close to it. Indeed, scientists found one high-speed star within M4 that was moving at about 200 kilometers per second, much faster than the average speed of stars in M4. This star was also located close to the center of M4, suggesting that it could have been ejected by an IMBH. However, to confirm this hypothesis, scientists had to rule out other possibilities, such as the star being a binary system or a runaway star from another cluster. To do this, scientists conducted simulations to explore the impact of removing the high-speed star from M4's core. They found that even after removing the star, the cluster still exhibited a similar mass excess at its core, suggesting that the mass was not concentrated in a single point, but rather distributed over a small region. This ruled out the possibility of the star being a binary system or a runaway star, as they would have a negligible effect on the mass distribution of M4. However, this also raised another question. If the mass at M4's core was not a single IMBH, could it be a collection of smaller objects, such as neutron stars or white dwarfs? These objects are the remnants of stars that have exhausted their nuclear fuel and collapsed into dense spheres. They are much more common than black holes and could also account for the mass excess at M4's core. However, scientists argued that this scenario was unlikely, because the space at M4's core was too small to accommodate many such objects. Moreover, if there were many neutron stars or white dwarfs at M4's core, they would have frequent gravitational interactions with each other, leading to an unstable system that would eventually collapse into a black hole. Therefore, the most plausible explanation for the mass at M4's core was that it was an IMBH, approximately 800 times the mass of the Sun. This conclusion was supported by theoretical models that predicted the existence of IMBHs within globular clusters. Moreover, this conclusion was consistent with previous observations of M4 that suggested a high concentration of dark matter at its core. This discovery is important because it provides strong evidence for the existence of IMBHs in our galaxy, and sheds light on their formation and evolution. IMBHs are thought to be the seeds of supermassive black holes, as they could grow by merging with other IMBHs or by accreting gas from their surroundings. By studying IMBHs, we can learn more about how supermassive black holes form and grow, and how they affect their host galaxies. However, this discovery is not definitive, as there are still uncertainties and limitations in the data and methods used. For example, there could be other sources of error or bias in the measurements of star positions and velocities, or in the simulations of star dynamics. Moreover, there could be other ways to explain the mass excess at M4's core, such as exotic physics or alternative theories of gravity. Therefore, astronomers aim to gather more data from future observations using more advanced telescopes, such as the James Webb Space Telescope. Webb Space Telescope will be able to observe M4 in infrared wavelength, which could reveal more details about its core and its potential IMBH. By combining data from different sources and methods, astronomers hope to confirm or refute the existence of an IMBH in M4, and to find more IMBH candidates in other globular clusters. Thank you for watching this episode of CosmicHuntX. If you enjoyed this video, please like and subscribe to our channel for more content on astronomy and cosmology. And don't forget to share your thoughts and questions in the comments section below. Until next time, stay curious and keep exploring.